about routing security. So first of all, this is a quick introduction. It's called Routing Security 101. This is a cutout of material we have for MANRS. We have material that goes from a 2-day course to a 1-day course, and then 4 hours, 2 hours, and then I cut out some of that material for a 1-hour introduction to routing security. There is a lot more to say, as MANRS has courses, both online and tutorials face-to-face to complement what is in this session. So I'll be happy, together with Robbie, later to post the links to our training courses, to post links to all the rest of the material we have. But for the moment, let's look at routing security. We have 3 major parts, and you will, if you've ever looked at MANRS as a project, you will recognize, you will maybe understand that there is a similarity between this scheme and what you've heard about MANRS. There is RPF, that is something that we use to filter what we get towards or from our customers. Then we have another pillar that is filtering, and that's something we apply with peering partners and transits. And in our growth path, we get to RPKI, which is something we can apply to the whole address space we see on the internet. So these are the 3 main areas we can concentrate on when we look at routing security, when we want to discuss routing security. RPKI is the most complex of these because, of course, it's global. It introduces more concepts that are, introduces, let me say, crypto, but it's just a verifiability of the data. There's nothing that's really encrypted. Everything is public, but you can verify the data you find. So it adds layers of complexity. Then filtering is a little less complex, but it's based on very old structure of databases, and we'll see that. And then RPF, which is in a way the simplest one of the 3 to implement, but on the other hand is the one that might carry more complexity. Why? Let's have a look at what it is first. It's called, it's a system that we use for doing anti-spoofing. So the idea here is that we might have customers, we might have people who are behind our network that get a service from us, who try to forge their identity in a way. Don't take my words for granted. In this case, it's what we're talking about here is, let's say we have a router that's connected to our network. That's at the customer's office, and that router gets in a way compromised, or our customer gets a software on one of their computers who starts generating traffic, which uses source addresses that are not coming from the address space that we have assigned to our network. If we don't apply RPF, chances are that that traffic will be originated by one of our customers, will get to our border routers, and will be just forwarded as it is out of our network to its destination. And then that destination will answer back. But then when the answer goes to what they see as the source of the packet will be another random address somewhere on the internet, not one coming from our network. So the responses to the packets that we send out of our network, that we allow to get out of our network, will be sent to a different network. This is how a lot of attacks are generated. So there is a way to avoid this, and one way is using RPF. There is reverse path forwarding, and there's a mechanism called unicast reverse path forwarding. So the concept is, let's check if an entry exists in the routing table before accepting the packet and forwarding it. So we add another step to the routing process in our routers. We have 4 modes of operation: loose, strict, visible path, and VRF. What does this mean? Starting from loose, basically, our router receives a packet, checks that an entry exists in the routing table for the source of that packet. If it exists, it forwards the packet. But now you can imagine that we might have a large network. And when we have a large network, we might have different routers that take care of different parts of our network that aggregate connections, especially when we think about national operators. You might have, I come from Italy, and Italy is usually divided into 3 large areas. So let's say we have a big aggregation router that takes care of northern Italy, a big aggregation router that takes care of central Italy, and one for southern Italy. I might, if I have a situation like this, accept to route a packet coming into my northern Italian router, but which was supposed to be originated by a network in southern Italy, just because I have that route in my routing table. So strict mode adds an additional part to this, where it not only checks that an entry exists in the routing table, but that route must point to the same interface where we have received the packet from. Packet on, sorry. So this means if I enable this mode on one of my interfaces, I will only let's say I have assigned a network to my customers. I will only forward packets that come exactly from that network. So this is the mode that is suggested to implement in most of the networks. Strict mode, RPF, towards on the router that aggregates our customers, and just towards our customers. So if our customers try to generate some traffic with a different source address than one that's assigned on that specific interface on that router that is to the interfaces connected to that router that's aggregating all our connections, let's say from northern Italy, then we will just drop it. And then we will not be generating traffic towards the destination, where the answer will go to some other network and will probably create issues on the internet. So there we go. Strict is what's recommended, but there is also feasible path RPF. And just to mention it, it's you check that an entry exists in the routing table or any other route not installed or not preferred. So it's something that says, if you know of a way to reach that network, let's just route those packets. And then there is VRF, where you check that an entry exists in the routing table and the route points to the receiving interface. It's similar to strict mode, but it's based on VRFs. So with this, many people have asked in the past, okay, I've tried enabling RPF on my routers. How shall I do this? So the recommendation that generally comes is to enable strict RPF towards your customers, and that's it. Do not try to enable loose mode on your transits, on your peerings, because that might lead to issues, or even strict mode. If you enable strict mode on a router, especially on interfaces that go towards one upstream, and then the packets come back from another upstream, you're just going to drop the packets incoming because the routing is asymmetric. And we all know that a lot of traffic comes via asymmetric routing. So just the recommendation is to not do that. So just enable strict towards your customers. And here we have an idea of how you can do that. This is over Cisco, where you just go into the interface configuration. You tell it, just verify the unicast source and reachable via the received interface. You can do it with Juniper. Juniper just has one keyword, RPF check. But another way you could do source validation in this case is using access lists. So you can use them towards servers, towards your infrastructure networks, or this was basically an idea that came up the early stages of, well, before even RPF was invented, because there was no such feature, no advanced feature as RPF. So you would apply just an access list saying, I only allow, like in this case, I only allow and permit certain source addresses coming on that interface. And then you apply that ACL to that interface. The difference between an ACL and RPF might be that the ACLs are more lightweight. So if you have routers that are already overwhelmed with lots of rules, lots of other configurations, ACLs might be a little bit more lightweight. RPF adds an additional checks whenever a packet hits the router, because you have to do a check of the routing table, and then checking where the packet came from, if it matches the interface that's going out. So RPF adds a little bit more work to every packet processing, while ACLs can be more lightweight. And you can take this example, which is for Cisco, or the example from Juniper, and basically convert it into any other system. Like you could do a firewall rule for IP filter on Linux, or any other firewall you can imagine, PF for those who use OpenBSD or FreeBSD, and so on. So this is a little simpler, but still does the trick. So choice is up to you, because this is, on the other hand, a little less flexible. If you keep adding or removing or moving networks from your border routers, you might want to have RPF. While if your configuration is mostly static and you know beforehand all the networks that will be assigned behind that border router, then fine, I would go for an ACL. So I hope there are no questions. I haven't seen anything in the chat so far, but now is your turn, because I need to get a bit of sip of water. If you have any question, just put it in the chat. And I still don't see anything. So let me go ahead. And if you still have any questions, you can still put them in the chat. So I told you there were 3 pillars. We looked at the first one, and I told you it was going to be the simpler one. Now let's look at filtering. Filtering are techniques used to decide what you want to allow inside your network, and especially what you announce to your neighbors. So you have to take care of what is coming towards you, but also what you announce to everyone else. Now, why is it important? Because it's your first line of defense. If you don't allow a network to get into your routing table, you cannot reach that. And so if that network is not supposed to be there, and you decided to not accept it because there is no data proving that that network should be announced by a certain ASN, or there is no data that says that that network should be in the routing table at all, then you just can drop the announcement, and no traffic will be available to run between your network and that network. And if that network really doesn't have to be there, it might be being used for, I would say, not good purposes. So it's good you are filtering it out. So you control what you are announcing, but remember that you have no control over what your neighbors, what the other networks are announcing to you. So you have to take decisions and decide how you want to filter. So what are your data sources? What are your sources of truth? The internet routing registries, you have bogons lists, and then an important source of information these days is PeeringDB, because that's where you can start your search for AS sets. And I have a small demo at the end of this section, so we can go through that then. So how do you generate a prefix filter? Imagine you have an AS set, and that is an example that we can also use later. You have AS 141384 : AS customers, and you have a bunch of members. Once you have the members, that's an AS set. It tells you that AS 141384 has these members as customers. So behind 141384, you should see AS 65530, 65535, and 65550. And how do you figure out what you should be filtering if you want to set up a BGP session with AS 141384? You take all the members inside the AS set, and then you do what's called a reverse lookup, or actually an inverse lookup. If you look the definition in the RIPE database, for example, and you find all the route 6 objects in this case. I like to use IPv6 as for examples, where the origin is one of those 3 AS members. So it tells us that AS 65530 should be originating 2001 DB8 column A, column B for the other AS 65535, and C 2001 DB8C/48 for AS 65550. With some tools, we can take these routes, generate the configuration, push them to our routers, and then have them filter exactly what AS 141384, which, by the way, is an ASN that we have at ISOC for some research that we do, what we should be expecting to filter coming from them. So how do I do this? I check the AS set, as I mentioned, walk the AS set, prepare a list of all the ASNs contained. If there is another AS set, because AS sets can be recursively put into other AS sets, just walk that as well. Just so create your full list of all the ASNs included in the direct AS set and all the AS sets nested into that, in all the what's called the customer cone. With that list, run an inverse query for each one and get all the route objects where they are listed for each one of those ASNs where they're listed as origin, which means that we should be expecting those networks to be originated by some customer or directly from AS 141384 or one of its customers. Now, what are the best practices? Don't accept bogon ASNs. First of all, we'll see bogons in a moment. Don't accept bogon prefixes. Don't accept your own prefix. That's actually something that's embedded already in the BGP daemons, which will just BGP software will refuse to accept its own prefixes. Don't accept the default unless you have requested that. If you accept the default, so 0/0 or 0/0 in IPv6, but I would like to use 2000/3 in this case, unless you have requested that specifically, don't accept that, because otherwise it will force you to send all the traffic, and also that one for networks that you don't know about, just as a last resort to one or more of your upstreams. So just don't do that. Don't accept prefixes that are too specific. And here I have a question. So let's spend a moment here. What is too specific when we look at IPv4? What is the limit we consider that's good in IPv4 for BGP announcements? And what is that we don't consider as good at the moment? Can you write it in the chat? Can you write in the chat what you think is at the moment, is the the prefixes that are too specific, what the limit is for prefixes. I don't see anyone for now. Okay, I see the first answer we get is perfectly correct. Oh, I like the second one. I like Musa. And so those are all three of them are good. So the limit for specific prefixes is a /24 now in IPv4. It's something that is, I wouldn't say set in stone, but it will take a lot to change that. For IPv6, we have /48. But what I always like to use as an example is, well, I have my own autonomous system. I have my own IPv6 allocation. I have a /29. Actually, I have two /29s. Yeah. Now, can you imagine how many /48s? Actually, let's see if you can write it in the chat. How many /48s do I have in my /29? Does anyone know? I'll give you a few seconds. I can take a sip of water in the meantime. Voila. It's a little bit more than 512,000, but yes, it's more than 500,000. Good answer, Oli. It's more than 500,000. So I have 500,000 potential IPv6 announcements in my /29. Then I have two of them. So potentially I have more than 1 million routing table entries waiting to be announced out of my address space. What if I was to create, I build a script that would go and create all the route objects needed. So 500,000 route objects in the RIPE database. Because I'm in the RIPE region, I'm based in Zurich, in Switzerland. So if I have my 500,000 IPv6 /48 route objects, and then I go on an internet exchange, I peer, for example, at SwissIX. You can look that up. I peer at SwissIX. So I decide, I wait a couple of days after I created my objects in the database, and then I write another script that pushes in my bird configuration all of the 500,000 /48s I potentially could announce, and then generate them as a BGP announcement, propagate it over SwissIX. What would happen? What can you imagine would happen? You think it would work? Do you think there's any way this could actually work? Is that do you think yes or no? Who is for yes? And more importantly, who is for no? I see Robbie saying yes. Potentially it would work. I'm not sure how many routers would have enough capacity to absorb those routes and then install them in their forwarding table. But yes, it should work. Now, I always use this example to say, for now, IPv6 is at a stage where a /48 is fine. I'm pretty sure in the future things might change, and I think we might consider moving to something different, something a bit more strict for addresses that are under big allocations, like the /29s or bigger. And then for all the other PIs, so the address space that was handed out as at least in the RIPE region, it's called provider independent. Those are smaller allocation. Well, those are assignments for a /48, or sometimes it's a 46, up to 44, something like that. But they come from a specific part of the address space. Then we might be less strict for that part of the address space, and then stricter for, I don't know, something like a /32 or 36 for the other part of the address space, so as to avoid situations like this one, where someone just decides to deaggregate their single allocation into 500,000 or 1 million or 2 million objects and related BGP announcements. So I would be curious to hear. Usually in a room, when I give this example, people's eyes just go, wow, I never thought about this, this opportunity, this chance. So I hope I have generated the same kind of reaction for you at home now. Now, going to the next part is don't accept if the AS path is too long. AS paths are usually 7, maybe 10 ASNs long. If you look at the actual routing table, you might see some AS paths being 50 or 70 entries, or some, I've checked, there are a bunch of them that are more than 100. They're generated by wrong configurations. Some vendors have a way of configuring what's called AS path prepending, where you put the prepend you want to have. So how many you put your exact prepend you want to have. In some other cases, you just have to put the number of prepends you want to have. But some people mix the configurations. So when they put the number of prepends, when they are supposed to put the number of prepends, they put their AS number, and then the AS number becomes the number of prepends. So some issues come out of that. And so I would suggest there is a common, like there was a discussion some time ago, and the agreement was that 40, maybe 50 is the acceptable length for acceptable. Like, let's say we can stretch all the way to 40 to 50, maybe AS path long. And then, so don't accept whatever is longer than that. There's no reason. And then create filters based on the IRRs, the Internet Routing Registries, because they are supposed to be holding the final truth about who is supposed to be originating prefixes, BGP announcements. But then there are some routing registries that are more reliable than others. So the regional registries, so one of the 5 regional registries are the ones I would trust more than others, such as RADB or AltDB or others. Yeah, so I mentioned bogons, and bogons are routes you shouldn't see in the routing table because they are either private addresses, space that is unallocated, or space that has been allocated to a regional registry but hasn't been assigned to the local registry or to the operators. And then you have reserved space. So addresses for documentation, for multicast, etc. Tim Cumry provides a list for both IPv6 and v4 that's updated daily. You can get it either as a file via HTTP. So you get the file, you look at it, it contains all the addresses that are not supposed to be seen in the routing table. Now, for v4, that's a short-ish list, because most of IPv4 has been handed out. So the list is relatively short. But for IPv6, IPv6 is a bit more complicated because, especially because IPv6 is being handed out, it's been assigned or allocated with what's called sparse allocation. So there is some space that is left between, in some registries, between one allocation and the other, so that instead of, if the operator grows enough, instead of getting a new network, when they go back to the regional registry to ask for more space, they're just told to change the subnet size, increase the subnet, well, increase the subnet size for their allocation, and that will be fine because some space has already been reserved in the past for them. So the list for IPv6 includes all these little holes between allocations. So it's pretty long. But what you can do with these lists is you can either get them via HTTP, well, HTTPS, you can get them via BGP. So they are updated frequently as new data comes in. And with BGP, you could receive them in your BGP feed and then set a next stop or black hole them. There's a lot of examples on the Team Cymru website, or you can find a lot of them on the internet as well. There are reserved ASNs that are also bogons, 0, for example, or 2, 3, 4, 5, 6, which is reserved for the transition between the 16-bit ASNs and the 32-bit ASNs. Then there are documentation. There are just reserved for private use. The last 16 and 32-bit ASNs are reserved, and then IANA reserved a couple of ASNs as well. So as you can see, we have a bunch of them, a bunch of ASNs that you should not accept in your routing table, and then you have prefix lists that you can build with the routes you want to accept or announce. Can create them manually or automatically, and especially with data from the IRRs. So I suggest using a tool. BGPQ4 is the latest and greatest. PEVAL is there as well. It's part of the IRR tools. And then there's the level 3 filter generator, which now is called differently. And I keep forgetting to update the name here, but it's an online tool. But I will show you mostly BGPQ4 because it's easy to use. It's available on all the platforms and generates filters for pretty much any platform you can imagine. And then if your platform, if the platform you use is not included in the ones that are already implemented in BGPQ4, you have a functionality where you can define how you want the output to be. So you can adapt it to your liking. So BGPQ4 is available on GitHub, but you get it as a package on mostly any operating system out there. It's written in C, uses the entity IRR as primary data source, which mirrors all the other RIRs. So it's fine. And as I said, Cisco, Juniper, Bird, OpenBGPD, MikroTik, they're all supported. There is also Nokia. I think there's, well, many others. So FRR as well. So you can use it for anything. And then you have to consider router provisioning. Prefix lists should be updated every day. Or when you get an email from one of your customers saying, hey, we have a new prefix, or we have a new customer, would you update your filters for us? I suggest having automated procedures. You can use netconf, or personally, I use Ansible. My routers are Bird, so I generate the configs in a central location, and then I push the configs to the different routers. And then pay attention, this is my suggestion, to consider all the cases in your procedures. I know of at least a couple of people who built their own tooling to generate the filters and do this and do that, and then they didn't consider the fact that sometimes your data source, as known as the databases, might be down, unreachable, or you might have any issues. So I know of cases where someone generated an empty config for prefix lists, basically filtering the whole address space out of their network. And then reconfiguring everything was, well, I wouldn't say tricky, but if you can't reach your routers from outside, you have to use an out-of-band solution to get to them. So I have a very quick demo for filtering here. So let me move to iTerm. I'm just preparing the terminal here and stop sharing my screen. Start sharing my screen with iTerm, and here we go. So this is my little terminal. I have BGP Q4 installed, and these are all the different options. So you can see that all the platforms are Nokia SAR, Arista, OpenBSD, OpenBGPD, Bird, MikroTik. I just copy pasted everything. I have HPQ4 again. There we go. And then I have a series of output modifiers and everything. Now, imagine you have someone like me, for example. My ASN is 58280 as a customer. Imagine you want to, well, as a customer or as a peer at an internet exchange, we decide to set up our BGP peering. So you would like to see AS58280. That is my ASN. And in IPv4, I have 1/22. What about IPv6? For IPv6, I have a /29, another /29, and then a more specific /32 as route object. So if you were to build a prefix list, you would have a way to do it here. But I have some other customers in my network. So you might want to check PeeringDB for that, because then in PeeringDB you would be able to find my AS set. So let me stop sharing this and sharing my other screen with PeeringDB. So I am on PeeringDB. I check for AS58280. Here we go. This is my ASN. You see I peer at a bunch of internet exchanges. And then here you see IRR and AS set and route set. So this is my, this is what you should be using as AS set when you want to peer with me. So AS58280 colon AS-Stucchi, which is my surname. So I'm copying this. I'm going to paste it into iTerm to here. So instead of that, I push my AS set. And you see that here we have a bunch more networks, because behind me there are a couple of I wouldn't say they're not customer networks, but they are networks who get some transit from my ASN. And the same goes for IPv6. For IPv6, there are a bunch of /48s, a couple of /29. We have a /52 that's there for as a test, because as I told you, we have a network that's for ISOC to do a bit of research. So if I check that object inside the RIPE database, you see that it's an AS set and members are series of ASNs, including 141384, which is the AS we have for ISOC research. When you create an AS set, don't forget to include your own ASN, because otherwise it doesn't get calculated into the origins. And here we go. So I showed you that if I wanted to build an prefix list for peering with my network, you would have to just copy paste this into your routers, or put BGPQ4 in the tooling so that you build a configuration that you then push to your routers. Exactly, Musa. I just saw your comment. This means that peering DB needs to be kept updated by operators with their customer code, not just with the AS set. Peering DB plays a very important role for also figuring out who is peering at a certain exchange, who is present at in a certain facility. So the more information you put into peering DB, the better your peering is in the long run, because you let other networks know that you are in a facility or peering at an IXP and so on. So peering DB plays a very important role here. So if we don't have any other questions or comments here, I would go ahead and move on to a very quick introduction to RPKI. Usually this takes probably a whole hour and a half, maybe 2 hours all by itself. So I'm trying to squeeze everything in the next 15 minutes. So bear with me. I told you that there are, when we route on the internet, we have BGP and we have networks exchanging reachability information. So in this case, network B says, hey, hi, network A, I have this network. I have 213, blah, blah, blah. And network A replies with, I have another one, 193. Blah, blah, blah. So the two networks have exchanged reachability information. But at this point, BGP was built with no idea of security in mind and no idea of trust. So both A and B are going to ask themselves if the data is correct, if there is trust that can be put there. So the solution in this case can be the IRR, the Internet Routing Registry, where in the RIPE database, but also in the ARIN database, in the AFRINIC database, APNIC and LACNIC, I can find information that help me figure out if it's okay to accept that BGP announcement from that specific network, or where I see that the origin is a certain origin. So it helps me in a way. Now, the problem is that some IRR data cannot be fully trusted. There is a lack of accuracy. Sometimes you have incomplete data. There's no maintenance. Me and Aftab, a colleague at ISOC, we have done a bit of investigation over this. So when I say that there are third-party databases that are widely used, the main ones we can think of are RADB, for example. And we did an investigation to check how much data you can find in the regional registry databases that you find either duplicated, so with the same origin in route objects, or with different origins, which is even worse, in, say, RADB. And the data is available. And if you, I'll show you my email address at the end of the session. So if you're interested in having a look, I can send you some links. But there are a lot of route objects that are duplicated between IRRs and RADB. And this, even if they contain the same data, that is not good. Because imagine you today operate one network. So you have your, let's say, like in my case, /22. But then tomorrow, you want to transfer that network to another entity. You transfer that network. The entity changes the route object in the regional registry. to point to their ASN as origin, but then they forget to, they don't know that there is an entry in RADB that needs to be also updated. So people who look at that data and try to trust it, they will be faced with, okay, shall I trust, with a question, shall I trust the RIR or shall I trust the RADB? Which one is correct? And they could make wrongful assumptions. Like they could trust RADB while the data hasn't been updated. So consider this and the fact that there is no verification in some databases about who holds these IPs or these ASNs. So there is a lot of data that you might not want to trust. So since 2008, all the regional registries started operating RPKI, which comes from standardization that comes from the ITF. So the idea is to take what we have in the IRR and add a way to verify that the data is trustable. So adding what's called crypto security, and this enables you to provide, to get data you can trust. Because instead of having more than 30 databases, you just have, well, one big database operated by the 5 regional registries. And so it's all in one, well, it's in a limited number of places, and it gives you data you can verify. So the goal is to tie IP addresses, so networks and ASNs, to also public keys. So there's a public key infrastructure that is set following the hierarchy of the registries. So there's no more, well, in this case, there isn't a third-party database that runs RPKI. It would be possible, but for now we don't have it, so it's not there for now. But it would be possible. And then what we get is basically a piece of data that says that the certain ASN is authorized to announce a certain prefix, and the signature comes from the holder of the prefix. So if I have a network, I can say, I authorized the ISOC research ASN to announce that because I want them to do so. And I can just do that. So the chain of trust is based on certificates, on certificate authorities. And basically, the RIRs have a way to have a certificate that covers all the resources, so 0/0. Each one of them has a certificate that covers all the resources. It used to be different in the past. In the past, the RIRs had just the coverage of the resources that they held. But then the thing is, in many cases, you can transfer prefixes, you can transfer networks between RIRs. So it's easier now to have 0/0 on every RIR's certificate. That is self-signed by its private key, and then every LIR, every member has its own certificate authority where there is a relationship with the certificate authority of the regional registry. So now we get to ROAs. Because when we look at RPKI, we have two sides. One is the signing, when you create your ROAs. So you create data for others to use. So you sign something. And then on the other side, you have the validation, where you verify the data that others have put in the database and others have signed. They are two totally separate actions, things, and one can happen independently of the other. especially in your network. You could be a network that just signs its ROAs and that's it, doesn't do any validation, or vice versa. You could be a network doing validation, but without signing your own ROAs. So how does this work? Let's look at the left side for now. Let's look at the signature and what a ROA is. A ROA is basically a file that puts together a prefix, so a network, and an origin. There's a little bit more. There's a little bit more spice added. I'll get to that in a moment. You have, in a ROA, you have basically a statement that says, as I mentioned already, this AS number, so the origin, is authorized to announce this prefix. So LIRs can create ROAs for their resources. Multiple ROAs can exist for the same prefix, even with different origin, different max length. Get to that in a moment. And of course, they can overlap. So when I look at a ROA, I have three pieces of data in it. I have the prefix, so the network for which we are creating the ROAs. We have the origin ASN, and this is what I had already mentioned, but we have a third data point in here, what's called max length, the maximum prefix length that a ROA is authorized to advertise. So you can have a prefix that is a /22, but then have max length, say, up to /24. So everything between a /22 and a /24 in that address space is allowed, for example. So this is an example. We have a prefix with a /22, but max length /24. So if we see in BGP an announcement that is for a /22, fine. /23s separate, fine. /24s, perfectly fine. But then when we go to /25, let's forget about the barrier of announcing a /25. Those are not good. So for a more detailed example, imagine we have AS2121, that's ripens C with a /21 of max length. There you go. This only these networks, only one network would be allowed to be announced. We have about 5, 7, let's say 10 more minutes. I'll stay large, 10 more minutes. So please bear with me. Thanks for the tip, Robbie, because I mentioned it at the beginning that it would take a little bit more than just 1 hour. So I'll try to speed up now. We have the /21 with a max length of /21. So we can only see, we would only be able to see a /21 there. Anything more specific is not covered. So if we want to generate more specific announcements, we would have to create another ROA. In this case, we create one with the /23, max length 24. So this will help me allow these three announcements to go through. I can do the same on another part of the address space, or a /23. Here, max length would be /23, so only one would be allowed, and there we go. So as I said, ROA can overlap. They can contain different origins. They can contain different max lengths. As long as one ROA in the whole set verifies the BGP announcement, then the BGP announcement will be fine. If none of them matches, then the network should not be accepted. Now we have a small issue here with max length, though, which introduced an issue with the chances that other networks could announce our networks as well. So imagine I have my own ASN, and I see that there is this this network that is announcing a /22 with a max length of a /24. And there is a /23 as well, but no /24 is being announced on the internet. So what I could do potentially would be to add this origin ASN to my AS set. wait a couple of days, set up a router behind my network as a downstream, for example, announcing that /24 or one of the /24s here that is not already announced on the internet. Now, the origin would be fine because the AS matches. The ROA says that that origin ASN is allowed to announce up to /24. So that matches. So everything is fine. So in reality, the BGP announcement would be perfectly valid. So how can I avoid this? Is by creating more strict ROAs with more strict behavior. So in this case, if I were instead to have the /22 with a max length of /23 and not open to /24, this would be invalid. This would not match the ROA we have on top. I hope this is good so far. I don't see any questions in the chat, so either you are too confused or everything's clear so far. I hope it's all clear, so I'll just go ahead. You have two ways of running RPKI. One is hosted, where the RIR does all the work for you. Especially the RIPE-NCC has full automation for this. So you just go in, push a button, and then you can just create your ROAs. You just focus on them. Actually, the interface is also very, very simple, in which it also tells you, okay, we see these BGP announcements from you. Do you want to match all the BGP announcements with ROAs? And if you say yes, then it just creates automatically everything for you. So you can focus just on the ROAs and publication and everything. Or you can do delegated RPKI, where you run your own certificate authority software. There are two so far, one from Dragon Research Labs, which is pretty old, still based on Python 2, and and the new version that's called Krill from NLNet Labs, which is a work in progress as well. So the NLNet Labs keeps adding features. So recently there was ASPA, for example, support for new types of objects and so on. You would have at this point to set up your connection with the certificate authority and then generate your certificate, get it signed, and blah, blah, blah. Now, the good news for delegated RPKI is that you have two components, one part where you sign your data and then one part where you publish it, which is done both with rsync and another protocol that's based on HTTP. You can also use, for example, in the RIPE region, you can use RIPE as your publication point. You can do a delegated RPKI, but instead of running your own web server, your own rsync server, you can just push your objects to the RIPE-NCC and they will publish them for you. Now, we have validators. So this is the other piece of the puzzle, and we're looking at the right side of the elements of RPKI. So now we see how we validate. The validators are a software that creates what's called the local validated cache with all the valid ROAs. So it means that it downloads all the RPKI data from all the RIRs, verifies the chain of trust. So it verifies that all the signatures are in order, everything's okay, the certificates have not expired, so on. And then this piece of software talks to the routers using a protocol called RPKI RTR. So basically, this is how it works. You have a file for every regional registry. The one for ARIN is not specified here, but there is one, of course. It's just that to get to use that, you have to acknowledge that how are they called? There's a accept an AUP, or there's anyway, you have to accept a clause and say, yes, I'm okay with this. So it is distributed now with the validators, but you still have to say, yes, I'm okay. And that data is downloaded by the validator. So the tal file points you to where the repository is, which server, and what the latest public key is for that repository. And then you download all the data into the validator. The validator does all the calculations, and then it provides that data to the router. So the router gets BGP announcements on one side, ROAs on the other, and when you match the data between the two, it helps get better routing decisions. So what are the options? You have Routinator, you have RPKI client, which is part of the OpenBSD project. You have Octo RPKI from Cloudflare, and then Fort from NIC Mexico and LACNIC written in C. And then last, we put all these pieces together. Basically, you get the validator to get all the data from the repositories, as we've seen a moment ago. Then you generate a validated cache. That validated cache is distributed to the routers. And then the routers make routing decisions based on the data they received from the validated cache. So how does this work? Imagine you have a validator which has a ROA, says AS100. That's supposed to originate 10/22. So here we have AS100 and AS200. Imagine AS100 announces 10.0.0.0/22. It matches the ROA, everything's fine. But what if they try to announce a /24 in that point? There is no ROA covering it. Actually, the one that covers it says it should be a /22. There is no max length specified here, so we assume that max length is /22, the same as the prefix. So that should be discarded, should be considered invalid and discarded. The same happens when AS200 tries to announce 10/22 because it is not listed as an origin here. So what are the states we have in RPKI origin validation? We have ROAs that get initially validated. And when we do a ROA validation, this happens in the relying part, in the validator, Routinator or RPKI client, or Fort, and so on. So there are two states. One is either valid, so the ROA gets put into what's called the validated cache, or there is the invalid state where the ROA just gets discarded. So at that point, the valid ROAs are pushed to the router. And when they match with BGP, as we've seen in the previous slides, if the prefix matches, if the ASN originating it matches, then the BGP announcement is valid. If there is anything outside of that, different ASN, different prefix length, and so on, the prefix is invalid, and then we should be discarding it. On the other hand, if we don't have a ROA, if we don't have data in RPKI that lets us validate whether a BGP announcement is valid or invalid, so we don't know, the holder of the address space didn't create a ROA, then we just consider it not found or unknown in this case. But what we can do is, and this is we still have a couple of slides, I'll be really quick here, is imagine you're in a situation like this one. You have 10/24 that's being announced by one of your customers, but they have created a ROA, or someone had created a ROA in the past for them for AS100 to announce just the /22, not the more specific route. There is an RFC that explains this, and this is a mechanism that's applied, that is implemented in all the relying parties, where you can create in the validator an exception, what's called an allow list or blacklist, or whitelist, where you say, hey, introduce this ROA artificially, push it to the router, so you could see that the 10/24 changed from invalid to valid. My suggestion is, if you ever do something like this, put a reminder for 2, maybe 3 days after you do this to check it again and remove the exception here. You don't want to have exceptions you don't control in your validators. So this was the last slide. I spent a little bit more. So we're almost 15 minutes past the hour that we had scheduled, but I hope this was interesting for you and I hope you learned something. I see a question. Before I go into the question, Robbie asked me to mention the two polls. There are two polls. One is, what was your biggest takeaway from this session? And I'm looking at Bram's, that's a comment actually more than a question, but you can quickly check your RIR data on various sources with IRR Explorer, which could help you cleaning it up. Yes. So if you have a look with, if you have a look at IRR Explorer, it helps you. And I guess, Bram, you're pointing to the entries for my network in, where is it? Because there is a, no, yeah, there is an entry in RADB. Yes. I'm keeping the entry in RADB as an example of how someone could create an entry for you without telling you. And so it's good it's there. I would like to keep it there. So I see we have some answers in the poll. Please take some time to provide us what your biggest takeaway from this session was. And while I wait for more answers, tomorrow at 7 UTC, there is another session where I will go a little bit deeper into how to set up ROV. So I'll go again a bit over RPKI, how that works, and then I'll give an example of how to set up ROV in a network. So that is what we'll be doing tomorrow. Maybe Robbie, shall we move to the second poll? Oh yeah, and then there is a tutorial on Wednesday about the MANRS Observatory run by my colleague Aftab. So it's a full week, and I suggest you check the whole agenda there for more information about what's coming next. So 30 seconds and the poll will be closed. And so please, if you can, provide some feedback there for us so that we understand if this was appreciated or received. And besides this, I'm not sure I have anything else left to say. Yep. Okay. Perfect. So we're sure we're saving the results of this. And do we have another poll, Robbie? There you go. So this is a very quick question. Will you be attending more sessions this week? We have a single choice. I see there's a very, very strong opinion towards, yes, we'll be attending more sessions. That's good. That's very good to see. So we're closing it quickly. There's just, these are called Bulgarian votes. So 100% voted for, yes, you will be attending more. So thank you for that. And I hope to see you again in maybe tomorrow or in future sessions. So thank you very much. I'll stop sharing for now. And I will mute myself.
Recording stopped.